Okay, so in 5.2, we just talked about how we can find the exact area underneath the curve using an infinite number of rectangles. But you can see in example number 2a, we're going to skip that long way. You're welcome. You guys lucked out. And we're going to talk a little bit about how we can go a little bit faster, use a trick to help us get there a little bit easier. And so for 5.2, example number 2b, it asks us to evaluate the integral by interpreting it in terms of area. And so I have a function, x minus 1, and I would like you to integrate it from -2 to 2. What that really means is that we have this graph, x minus 1, and I want you to find the area underneath the curve and the x-axis between -2 and +2. So what I did is I kind of graphed this. I knew this was going to be a linear equation, y equals mx plus b, with a y-intercept of -1 and a slope of +1. So I kind of sketched the graph. And I noticed that the pink area was the area underneath that curve between the curve and the x-axis. If you notice on this side, some of the area is above the x-axis, but on this side, the left side, some of the area is below the x-axis. And we talked in our last video about being positive versus negative. So when we go to find the area, what we can do, instead of doing a bunch of rectangles and getting an estimate, we're going to actually find the exact area on this one because we're able to kind of separate it into exact triangles and find the area, the exact area of those triangles. And so instead of doing rectangles, we're going to do triangles on this one. And if you notice that I have a base times a height divided by 2. I have a base times a height divided by 2. So I can find the exact area of these two triangles, so I can find the area underneath the curve. Okay, and so I ended up getting a 1/2 here, positive, and I ended up getting a -9/2 there. Remember, negative is below the x-axis. And so when you add them together, you end up getting, what is that? A -8/2, -4, correct? Okay, so if I did it in terms of area, and I can separate my areas into exact geometric shapes, triangles, then I can find the exact area underneath the curve. But functions aren't always nice straight lines with cute little perfect triangles in there. And so how can we find the exact area without, and if we can't, separate it into a bunch of different perfect little triangles or rectangles or whatever it might be? Well, look what I did here. I took my function and I integrated it. I found the antiderivative of x minus 1, which is x squared over 2 minus x. And what happens then if I plug in my 2, if I plug in my -2? So I took my antiderivative, I plugged in 2, and then I plugged in -2. So I plugged in 2 here, I plugged in -2 here. What ends up happening? You see what I got? I ended up getting -4. Well, isn't that the same thing that I got when I found the area using triangles? And so again, finding the area underneath the curve is the same thing as integrating it from a to b. And it's the exact area. And so if we can't, on the next example, take our function and do a whole bunch of cute, perfect shapes, we can still find the exact area without doing an infinite number of rectangles by just integrating it and figuring out the value from -2 to +2, or from a to b. Okay, so properties of integrals we're going to talk about a little bit is how can we use this idea that integration is the same thing as finding the area underneath the curve. Okay, well, look at these few properties with me. If you look at the first one here, it asks us to integrate f of x from a to a. And so what that really means is we're finding the area underneath the curve of f from a to a. Well, think about it. If I have a graph and I ask you to find the area underneath the curve from 1 to 1, well, if you're starting at 1 and ending at 1, haven't you gone nowhere? There should be no area underneath the curve if you haven't gone anywhere. So if I ask you to integrate from 3 to 3 or 1 to 1, really your answer should always just be 0 because there is no area underneath the curve. Okay? So the second property here says that if we're trying to integrate, find the area underneath the curve from a to b, maybe we don't know the whole entire area from 1 to 3. Maybe we only know it from 1 to 2 and then from 2 to 3. Well, if I know 2 little pieces, can I take the 2 little pieces, add them together to get the big piece? So what this is saying is that I can find the area from A to C, then find the area from C to B, and that should be the same thing as finding the area from A to B. So the two little pieces should add up to the big piece. Okay? My third property here says that if I have a whole bunch of different functions and I want to find the area from A to B, instead of doing the combined function, what I should be able to do is find the area underneath f of x, integrate it from A to B, find the integral of g of x from A to B, and then add them together. Okay, so the little pieces separately. On this next one here, if you look really carefully at the limits of integration, they're called, it's backwards, right? Normally we go from A to B. We always go from left to right or least to greatest. And so when we have something that looks like this, where the limits of integration are flip-flopped, then we need to flip them back to the right direction, from left to right always, but then we need to make sure that we negate our answer. So if I were to ask you to find me the area underneath the curve of our function, I don't know, from 5 to 2. We normally don't go from 5 to 2, from right to left. We go from left to right. And so we would have to change this into finding the area from 2 to 5, which is the same area, right? But we need to negate our answer. Okay? All right, the next one says that if you have a constant, remember we can take that constant out, we can find the integral of the rest of it, and then just multiply it back by that constant. So a couple different properties of integrals that you need to know for a couple of the next examples.